So the real numbers are uncountable, so they cannot be written as a countable union of points. That is clear enough. But something that seems intuitively clear is if I take R2 and I take a countable union of lines, they cannot fill up R2. And the same in general, if you take strict subspaces of a vector space, they can't fill it up. Cardinality doesn't help here, but there is some nice mixture which helps, what is called bare category theorem. So let's for throughout let X be a complete metric space. Now what is it about the lines that we have? Well, they are nowhere dense, their complement is dense. So indeed this is the following theorem. We'll prove instead a slightly stronger theorem, which is the obtained by taking complements and deduce this, but the theorem is that X is not the countable union of nowhere dense closed sets or subsets of X, of course. So I'm saying closed here, this is sometimes emphasized, but the way we have defined nowhere dense, it's saying the closure is dense. So if it's not a union of closures of sets, it's clearly not the union of sets. But so nowhere dense means the exterior, which is the complement of the closure, which is open, is dense. So real line in R2 is nowhere dense. So countable union of these will not give you all of R2 for any complete metric space. By the way, if you have discrete points, this will be still true, but you'll just not get the nowhere dense hypothesis. So what we do is we look at the complements of these closed sets or closures of the given sets and instead prove the following theorem of Baire, from which this follows, and which is sharper. So not being a union means the intersections of the complements is non-empty, but in fact, if let me emphasize countability by writing if un and in n is a countable collection of open dense sets, then the intersection of un and in n is dense. Okay. So here we are. So the proof of this is that, okay, it's quite easy actually. You're given a point. Okay, so we want to show it's dense. So let's take an open set. Okay, so let V contain then whatever X be open. Okay, and then we take a point in that and we take a ball which is small enough so its closure is also contained here. Namely, I take a ball and take a smaller ball. Okay, so let B1 or let's call it B0 contain in V, be a ball, open ball, such that B0 bar is contained in V. Okay, now B0 is open and U is dense. So as U1 is dense, each UI is dense, there exists, let me say, X1 contained in U1 intersection B0. Okay, and B1 open ball containing X1, and again by making it slightly smaller than needed to be in this, such that B1 bar is contained in U1, which remember is contained also in V, so it's contained in U1 intersection V. Okay, so now similarly, now so we had this original open set, we found the ball, and then inside that we're finding another one. Now we'll take a point inside this and find B2. So again, as U2 is dense, okay, there exists X2. So and the B1 contains this X2 and B2 open neighborhood such that B2 bar is contained in B1. So we have smaller and smaller balls, which of course, so this is contained in, sorry, not just contained in B1, but it's contained in B1 intersection U2, okay, and which is contained in U1 intersection U2 intersection V, okay. So we inductively get obtain xi and bi, okay, and we can also ensure the diameter of bi goes to 0, because we can always check smaller balls, even if the smallest ball possible does not go to 0, okay. So then what happens is then xi is Cauchy. This sequence is Cauchy, as it is eventually in the ball Bn. So completeness says so convergent to x infinity, say, and x infinity is in the intersection of all the balls, but bi bars, at least their closures, because each xi is in the ball, and so in the closure of the ball, but this is contained in the intersection I equals 1 to infinity of ui by construction. So that's done. So, intersection V. So it's so the intersection of ui's with V is, the intersection of ui's with V is non-empty. It contains the point xi. So since V was arbitrary, this is dense. Okay, so we had to show this set is dense. This set is the same as this set here.